from Universidade Federal de São João del Rei. He's talk about relating second-order geometry of manifolds through projection and normal section. Thank you.
Thank you, Ingrid, and thank you for the kind invitation. It's a pleasure to be here, and especially to talk here at the Monte Olimpo of mathematics. So I'm going to talk about second-order geometry of manifolds. We're going to talk about them using projections and normal sections. We'll see how it goes. Those are the contents of my talk. So the very first question one might ask is, why the hell are you studying this? Well, our goal was to relate the geometry, the second-order geometry of three manifolds in Euclidean spaces with the second-order geometry of regular surfaces in Euclidean spaces. For here, notice I'm talking about regular manifolds. But also, in the singular case, the geometry of singular tree manifolds in R5 and the geometry of core-1 surfaces in R4. Here, when I say geometry, I'm talking about second-order geometry. That means I'm concerned about the second fundamental form and its consequences. Very well. For the case where K is 3, we're going to close that diagram and obtain something like this. So we're going to relate all the second-order geometries here with normal sections and projections. Very well. A little bit of history. For regular surfaces, for every regular point, we can relate a curve called the curvature ellipse. This curve is the image of the unit tangent vectors via second fundamental form. This curve could be an ellipse, a segment, or even a point. For core-1 surfaces in R3 and R4, the first fundamental form that we define in the singular points, the first fundamental form is not a metric. So it messes up a little bit the geometry. So for those surfaces, we don't have a curvature ellipse at singular points. We have a curvature parabola. But it's the image via the second fundamental form of the unit tangent vectors. Very well. And this curve could be a parabola, a half line, a line, or even a point. This curve was defined by Luciana Martins and Juanjo Ballesteros in 2015 for core-1 surfaces in R3, and by myself, who was AKA Cidinha, and Osset Sinha in 2019 for the case where n is equal to 4. A little bit of tree manifolds, regular tree manifolds. We'll consider, here I forgot to explain the notation. When I write reg here I'm talking about regular objects, and this is the dimension of the object. So this is a regular tree manifold. So we're considered tree manifolds in Euclidean spaces, F and immersion. For every point, we have a tangent space of dimension 3, and the normal space with dimension k. We have a second fundamental form defined in the tangent space in a canonical way. It's the orthogonal projection of the second-order derivative into the normal space. And for every point, we can define the curvature locus, a similar of the curvature ellipse, but for tree manifolds. So the curvature locus is the image of the second fundamental form of the unit tangent vectors. Since my tangent space has dimension 3, the subset of unit tangent vectors is a sphere. Binotto, Costa, and Romero Fuster, they showed that if this space has dimension 3, we have a list of topological types for the curvature locus. Those are the substantial possibilities. When I'm saying substantial possibilities, I'm saying that the Gaussian curvature is different than 0. So we have a Roman Steiner, a cross-cap, a Steiner of type 5, or a cross-cap. Those are the substantial cases. We have planar possibilities as well. Those are the planar possibilities for the curvature locus. Very well. A little bit of singular tree manifolds in R5. To study the second fundamental form, the second order geometry of those objects, we'll do a little construction to help us out. First, we'll consider a regular tree manifold, a local chart of this manifold, a smooth corank 1 map G, a point P here in the singular corank 1 singular tree manifold will be the image of this map G at the point of corank 1. And F will be taken as this composition as a local parametrization of the singular tree manifold at the singular point. Why the hell do I need that? Two main reasons. First of all, I have to be sure that this object is indeed a corank 1 tree manifold. And when I do such a construction, I make sure of that. And the second reason is, since this object is singular, its tangent space has dimension 2. But to prepare a good second-order geometry for this object of dimension 3, I should need a 3-dimensional tangent space. So, what will I do? I will use this manifold, and I will borrow its tangent space to construct my second-order geometry. This way. P will be always a point of corank 1 of this tree manifold. As I said, my tangent space has dimension 2, and my normal space dimension 3. Since this point P is the image of this point Q, Q belongs to M tilde, this tangent space, since it has dimension 3, it will act as my tangent space of the singular manifold. So I will use this tangent space to define the first fundamental form, the second fundamental form, and so on. The first fundamental form is defined in a very canonical way, but since this map has corank 1, this is not a metric, but a pseudometric instead. And taking a basis of this tangent space here, we can write the coefficients of the first fundamental form in a very canonical way, as we do for regular surfaces, for instance. And we can write this quadratic form in a very simple way, using the coefficients of the first fundamental form. The second fundamental form, also defined in this space, we define in the basis of the tangent space as the orthogonal projection into the normal space of the partial second-order derivatives of the parametrization in a very simple way. And we can extend to the whole space in a unique way as a symmetric bilinear map. This second fundamental form, does not depend on the choice of the local charge of the tree manifold. So my second fundamental form is well defined. Taking a normal vector, we can define a second fundamental form along this direction in a canonical way. And taking coordinates, we can write the coefficients of the second fundamental form in those coordinates. Also in a very similar way as we do for regular surfaces in R3 and R4, for instance. And fixing a frame of an orthonormal frame, actually, of the normal space, we can write the quadratic form associated to the second fundamental form as this, using the second fundamental form along each normal direction of my normal space. To define a similar object as the curvature ellipse, the curvature parabola, or the curvature locus for three manifolds, we have the following. We'll consider this CQ the subset of unit tangent vectors in my tangent space. In the regular case, we had the sphere, because we have a metric there. But now I don't have a metric anymore. I have a pseudometric. So the unit tangent vectors under this pseudometric is not a sphere anymore, but a unit cylinder. So this infinity doesn't stop. It's a unit cylinder in this space of dimension 3. So we'll define a map from the cylinder to the normal space. That is just the second fundamental form applied in the vector u. The image of this cylinder will be my covered curvature locus for my singular tree manifold. And if we write the parameterization of this tree manifold in a Monge-like form, we can parameterize the We can parameterize the curvature locus in this way, and taking in some Monge parameterization, the unit cylinder will be just like that, with the direction here being the z-axis. So I can write a parameterization for my curvature locus. CQ will be the cylinder. And this, was an adaptation for what Luciana and Juanjo did and for what we did for surfaces. Very well. Some examples. If we take this parameterization for the tree manifold, we have that the curvature locus is a parabolic region. We can have also a plane as the curvature locus, a half line, a line, a point, or even a paraboloid. So one might ask very naively, well, are those all the topological types? Hell no. This is not so easy. Until now, we don't have a complete list of all the topological possibilities we could have. It's a work in progress. And we can have more interesting examples as well. For this immersion, I have this curvature locus. It's a singular surface. Very beautiful one, actually. We can have also this one. Also very nice. This one. And what happens is, we prove that consider the action of the A2 in this space, the space of two jets from R3 to R4, R5 of core 1 map germs, we have 6 orbits. What happens is, for the case where we had surfaces, the A2 classification here used to distinguish completely all the orbits. So if we had the first orbit, the curvature parabola will be a parabola, the second orbit a half line, the third orbit a line, and the last orbit, the curvature locus would be a point. And it was a complete topological classification in a sense. So we could ask, what about now? Well, it doesn't. What happens is, for instance, this one, the curvature locus, as we saw before, is a paraboloid. This one, it's a singular surface. So they are in the same orbit under this equivalence. However, the curvature loci, they are not topological equivalent. But we managed to get a partial result when our parameterization of the singular tree manifold has this special look. Notice that we don't have x squared, xy, or y squared, so it's a very particular case. In this background, we have those equivalences. The first orbit, the curvature locus is always a substantial surface, but could be any substantial one. The second orbit, a planar region. The third orbit, a plane, a half line, a line, and last, a point. But it's a particular case. Nevertheless, an answer. So now let's see how normal sections work. We'll start first in the regular case. We'll consider a regular tree manifold and a tangent direction of this manifold. We'll consider this hyperplane orthogonal to this direction. And my normal section, the normal section of the tree manifold along this direction will be a regular surface given by this intersection between the tree manifold and this hyperplane. So it should be a normal surface contained in a copy of our 2 plus k. So one might ask, is there a relation between the curvature locus of the tree manifold and the curvature ellipse of the surface given by the normal section? And the answer is yes, there is a relation. We proved that if we have a regular tree manifold, the curvature locus of the manifold will be generated at each point. The curvature locus will be generated by the union of all curvature ellipses of all possible normal sections of the manifold. Very well. Let's see some examples. For instance, the curvature locus of this tree manifold is a Roman-Steiner. The first one that appeared in that topological classification. Taking some normal sections, we'll have those curvature ellipses. Notice that we have some ellipses, but also some segments as well. A case of a planar region. For this tree manifold, the curvature locus is an elliptic region. And here we have some possible curvature ellipses contained in the curvature locus of the tree manifold. Again, okay, we did it for regular tree manifolds. What about singular tree manifolds? Here the same happens. We'll have a singular core-rank 1 tree manifold. We'll define in the same way a normal section along a tangent direction. It will be now a singular core-rank 1 surface in a copy of R4. And we have the same exact result. So the curvature locus of my singular tree manifold will be generated by the union of curvature parabolas in all tangent directions obtained in taking normal section in all tangent directions we can. Very well, some examples for this tree manifold in R5. We have this is the curvature locus. This is the curvature locus of the tree manifold. And here's some curvature parabolas of normal sections. Another case, the curvature locus is this planar region, and here we have some parabolas of normal sections. Very well. Now we know more or less how it happens, how is the relation between the curvature loci between a tree manifold and its normal section. We'll now see how we close this diagram. We will start with a regular tree manifold. Sorry. Here, what happens is, since we didn't have a total answer for the A2 classification, here we have another partial result, how to see the difference between the A2 classification using the normal sections. So what happens is, if my 2jet of the parameterization is A2 equivalent to the first orbit, my curvature locus will be generated exclusively by non-degenerate parabolas. If we are in the second orbit, parabolas and half line, the third only lines, the fourth half lines, lines and point, and only points. Then again, a partial result, but nevertheless a result. Now the diagram. We'll start with a regular tree manifold in a Monge form. We'll start with this vector. This tangent direction could be any tangent direction, but this one is easier to work. and everything is rigid, we can make rotations and put the direction where I want. We'll consider pi v a projection along this direction, a normal section given by this hyperplane. I2 and I1 will be immersions, and v prime will be the corresponded tangent vector of this surface. Then we have this diagram, a commutative diagram with normal sections and projections. And what happens is, well, this surface is the normal section of this 3 manifold in this direction, and this one the correspondent. And what happens is, besides the commutative diagram of the 3 manifolds, we also have a commutative diagram amongst the curvature loci of each one of our manifolds. We'll see how it happens in an example. For instance, taking this example, then again, this tangent direction, this normal section, this is the parametrization for the singular 3 manifold, the regular surface, and the singular surface. We'll see what happens to each curvature locus. We have this. For the regular 3 manifold, the curvature locus is a Roman-Steiner, and for the singular 3 manifold is this singular surface. For the singular surface, the curvature locus is a parabola, and for the regular, an ellipse. This means that this is one of the normal sections obtained here, and this for here. And we also got a way to go from each one of these parametrizations to another using that diagram. So using that diagram and the diagram of the curvature loci, since the curvature loci in each possibility, it contains all the second order geometry of those objects, and they are all related, this means that all the second order geometries here, they are all related. This is a consequence of the curvature loci. Very well. We'll study a little bit of asymptotic directions for singular 3 manifolds, since for regular 3 manifolds it's already done, and we will relate all of them. So a direction in the tangent space, notice that I'm using the tangent space here, the cylinder. A direction will be asymptotic if we can find a non-zero normal vector satisfying this condition. It's the exactly same condition for regular 3 manifolds for regular surfaces. The definition is the same. And this direction V will be called, this direction E actually will be called the binormal direction. Dreibelbs defined a matrix such as we will do, taking a basis of the tangent space, a basis of the normal space. We can write this 3 by 3 matrix where each element is given by this relation. What happens is a direction will be asymptotic if and only if the determinant of that matrix is 0, or if we have a direction in the normal space such that the high function has is worse than Morse. So if the direction belongs to the kernel of the high function. This result also holds for regular 3 manifolds. And we have some results also. Considering a tangent projection, this point P will map to this P. This is a projection in a tangent direction, since here we have a regular 3 manifold, here a singular 3 manifold. What happens is a direction will be asymptotic here if and only if it's asymptotic here, which means that I can relate the asymptotic directions of those two objects. Also, the binormal directions, they are also the same for the regular three-manifold and the singular three-manifold. Again, if we have a regular manifold here, notice that it works for any dimension. Projecting along a tangent direction in a singular manifold here, this direction of projection, that means the direction I'm projecting into will become the new tangent direction of the singular projection. What does it mean? This new tangent direction is the tangent direction which is new under the pseudometric defined by the first fundamental form. In this case, the direction will be this one. This is not a new direction in our sense. However, in the sense of that pseudometric defined by the first fundamental form, this is a new direction. So if we project a manifold, a regular three-manifold, along the direction, a direction U, say, this direction will become this direction here in the cylinder. And as a consequence, the direction projection is asymptotic if and only if the new tangent direction is asymptotic. It's a consequence of those previous two results. So if we project along a tangent direction that is also asymptotic, this direction will become the new tangent direction here in the singular case. And when the new tangent direction in the singular case is asymptotic, we call it infinity asymptotic direction, and we denote it by U infinity, just a notation for the case. And what happens is, for singular surfaces, this direction was never asymptotic for non-degenerate curvature parabolas. So if at a point the curvature parabola was indeed a parabola, this direction was never asymptotic. However, for the degenerate cases, the half line, the line, and the point, it was always an asymptotic direction. So notice that it was an asymptotic direction if and only if I have a degenerate curvature parabola. Here, it doesn't happen exactly the same. For instance, before a proposition. This direction, the new tangent direction, will be asymptotic if and only if the two jets of the projection along this direction is not in the first orbit. It also happens when we project a regular surface in R4 to a singular surface in R3. The direction of projection was asymptotic if and only if the two jets of the parameterization in the singular case was not a cross-cut. It happens more or less the same here. So, what happens is, for instance, this regular three-manifold in R6, the new tangent direction is an asymptotic direction of this surface. And the two jets of the parameterization of the three-manifold obtained as projection is not in the best A2 orbit. But it's also an asymptotic direction of the singular three-manifold. So it doesn't happen the same as did for surfaces. So what happens is, since the curvature locus is substantial for this case, we have to define the image and the tangent space for the infinite tangent direction, even for the cases of singular three-manifolds with non-degenerate curvature locus. which didn't happen for surfaces. The definition is quite long and very technical. I didn't put here for a question of time, but there is a possibility to define it. And what happens is, if we take a tangent direction in the cylinder or the infinity tangent direction, this direction will be asymptotic for the singular tree manifold if and only if the image of this vector is either tangent to the curvature locus at the point, or the curvature locus is singular at that point. This result also holds for regular tree manifolds. Very well. Taking now we have seen how we relate the asymptotic direction of these objects. We will now see how to relate asymptotic direction of those two objects. So if we take a singular surface given by a normal section of a tree manifold in R5, if those two spaces are equal, what means? This space is the affine space, the smallest affine space that contains the curvature parabola. And this one is the smallest vector space that contains the curvature parabola. If they are the same, which means if this affine subspace is also a vector space, if they are the same, what happens is a direction will be asymptotic for the tree manifold if and only if the correspondent one here will be an asymptotic direction of the surface. Which means now that I know how to relate asymptotic directions here and here. Well, one might ask, what about here? Asymptotic directions for regular surfaces in R5 and singular surfaces in R4, or even here. What happens there? Well, there is a tiny problem. For regular surfaces in R5, the concept of asymptotic direction is not a concept of the second fundamental form. So with our machinery, we cannot relate these objects. So we are a little stuck. And for future projects, Cidinha, myself, and Raul, we're trying to classify the topological types of the curvature locus for regular tree manifolds and also for singular tree manifolds, trying to obtain a better answer for that unanswered questions that we had before. We didn't have a complete result, a complete classification. So we are in this task to obtain. Thank you very much.